Just about there, folks. Welcome back, everyone. Before we jump into section 7.3, any questions that folks would like to start us out with today? Okay, well, I don't have too many more announcements. We finished section 7.2 last week, or not last week, last Monday or Tuesday, must be the end of the week. And so assignment number 9 is now on the table. And we should be able to finish section 7.3 today. So that should be the due date, Thursday, April 4th for that assignment 10. I also posted the section 7.5 on equations just as a preview, but if we have additional time, we might take a look at that document down there. And as for what's going on further down in the schedule, let's take a look. We're having a third exam Tuesday, April 16th. And so that's going to be, let's count them, Tuesday, April 16th. That's going to be just a few weeks away. So still a good amount of time. I'm going to try to post information a little bit earlier on this one, what the exact coverage will be and those kinds of things. But we still have a good amount of breathing room before that third exam comes up. Also, we'll be allowed to use calculators on this exam. And so we'll start to use calculators a little bit more, particularly when we get into chapter 8. Well, this is the last section of chapter 7, so we're just about done with analytical trigonometry. Pretty much what happened in the course is chapter 5 is just defining the trig functions. Chapter 6 is graphing them. And the real purpose of chapter 7 is solving equations where we have to use everything we did above, trigonometric identities and so on. So this is almost kind of a review section in a certain sense. Well, any questions at all, folks, then, before we jump back to 7.3? Okay, in 7.3, we took a look at these identities. The double angle identity for sine, double angle identity for cosine, related identities down below. The two right here are the more commonly used ones, like we mentioned. And now we're going to the half angle formulas. Notice there are a lot of half angle formulas, but just like before, here's the standard one that you'd almost always use for sine. This is the standard one you'd want to use for cosine. But the one for tangent alpha over 2 as a half angle formula has 3 different options. Now that's kind of weird in a way. But when I wrote the notes for the course, I did not include this one, because if you go with this option, you have to simplify it, and that could be a fantastic amount of algebra and creativity just to simplify that thing. So I pretty much just picked between the last two right here. I felt like if we're going to use this half angle identity, it's a good idea to just focus on one of them. And so that's why I only brought one into the notes for the course. We'll use this version right here. So that's how the half angle identities work. And it's going to enable us to calculate some really interesting things, like say, we can now calculate sine 9 pi over 8 with that half angle identity. But first, we'll practice with it on this problem right here. It says, given a sine value, sine theta is -1/10, and this looks like it terminates in quadrant 4 based on that information. We want to calculate 4 different things altogether. So it looks like a lot. But really, if you're going to start with this one, sine theta over 2, you'd be using that identity. So you need a cosine value right away just to get started. So for a problem like this one, I would consider step 1, just find your cosine value based on sine. Yeah, that can get a little bit sideways for the inverse function. Usually that's going to try to simplify it to give you, like you mentioned, something irrational. But what we can always do if we need an exact form is use cosine squared theta plus sine squared theta equals 1. So that's always available to us, the Pythagorean identity. We do have the value for sine squared theta. So on the next line, it becomes cosine squared theta plus, in place of sine squared, put in that -1/10. Square that thing and set it equal to 1. So now this right here is going to turn into 100, and we get cosine squared theta plus 100 equals, standard thing I do is just make that have the same denominator. So let's call 1 100 100ths. And now we can subtract on the next step. So we now have cosine squared theta equals 99/100 upon subtracting. Almost there, we just have to take the square root, but we always run into the same issue. If we take a square root, there's two possible signs. We have that cosine theta is plus or minus the root of this whole thing, but I want to break it up because we probably do want to simplify this one. Also, you should use an equal sign. That's the standard thing to do. Let me squeeze that in. Equals a plus or minus root 99 over square root of 100. This one is a good one to try to simplify a little bit further because we're going to be putting a cosine here, here, and here. We might as well put in the most simplified version of that cosine evaluation just to make it all a lot less tedious. Yeah, now we have to go to right here, absolutely. So let's draw our just standard unit circle to get to this portion. That one's kind of wonky, but that's okay. It says theta is sandwiched between 3 pi over 2 and 2 pi. So the first thing we want to do is just plot these. 3 pi over 2 is down here. Forget I have to not be an equation field to draw. 2 pi is way out here. And so our theta value is just somewhere in the middle. No clue where. I'm just going to draw it randomly. About like that. Yes, the first coordinate will be cosine. Exactly. In this quadrant 4, we get a positive for cosine. That tells us we're using the positive root on the next step. Well, any questions at that moment, folks? Determining the domain for theta? Okay, I'm going to take this as a screenshot just because this problem is a lot longer than it looks. Let's put it down here so we have our formulas available as we go. So far we have cosine is positive here. Let's start simplifying this a little bit further. Root 99 can be broken down as root of 9 times 11. Square root of 100 just turns into a 10. And so now altogether, cosine theta is, back in the root, we'll take 3 root 11 over 10. So now that cosine theta is there, we're in business. We can start calculating sine alpha over theta over 2, cosine theta over 2, tangent and cotangent. But I would consider this to be the crucial step. But if you did make a mistake here, maybe you got just 3/2 or something like that, that's actually okay. You might lose points in the one spot, but you get partial credit for everything else if you apply the formulas correctly. So now, after that step one, for the next steps, we're just really evaluating everything else. Let's do sine alpha theta over 2. By formula, it's plus or minus square root of. With the sign involved, it's always going to be a minus cosine. So this will go minus cosine theta divided by 2. Okay, I want to pause right here because there's a really good thing to keep in mind that I'm going to remind us about in the next problem. It is actually kind of confusing, but for the half angle formula, the reason it's called that is because you have half the angle here, but when you go to use the half angle formula, you double the angle. That'll be an important reminder for the very next problem where we're going to double 9 pi over 8 to use the formula correctly. So that's our setups just so far. Now, there's a new danger about this. Notice up on my sign chart, that's a sign chart for theta, but we are not using theta. This is a good time for color coding. This is the confusion of the problem. We are using theta divided by 2. We need a brand new sign chart relative to that angle. So right here, this doesn't do anything for us on plus or minus because the plus or minus depend on the actual angle you're using, theta over 2. So here's the next thing we have to do. We're going to go over to the 3 pi over 2, less theta, less 2 pi. And we need to fix this. We need to make it look like a theta over 2. That's not so bad. You just take every single side of this triple-sided inequality, divide by 2. On the far left, division by 2 is the same as a half, multiplying. Just looks a little bit nicer that way. Less than, now you have to divide the middle by 2. And now you have to divide the right-hand side by 2. And again, the only reason we did that is we have to involve theta over 2 to get the right sign. That's the most confusing part, in my opinion, with the half-angle formulas. And that's the reason why I only put this one down for tangent, because it eliminates the massive confusion of which sign are you actually picking. That's a little bit tricky. But so far, here's the process. To get the right sign, just take your theta, divide it by 2, and you get to here. Does that make sense to that stage? Awesome, glad to see that. So let's now simplify this a little bit further. So back over here, this is just 3 pi over 4. Now less than theta over 2. Now less than pi. We already have a unit circle over here, so let's take this and bring it back up. But first, well, 3 pi over 4 would be somewhere over here. Pi is right over here. And so our angle theta divided by 2 would be somewhere constrained between these two values right here. It should look about like this if I drew it perfectly. I didn't want an arrowhead on that. Let me try again. So right here is theta over 2. Because we're doing the sine version, what would you all say? Is this going to be positive or negative when we go to select the root? Any volunteers on Zoom or in the class for which root we should take? Absolutely. And it's weird, right? Because if you use theta, you might have said negative, but that's the wrong angle. We have to use theta over 2, which is way up here. And like you said, that comes out as positive in this location, negative in that location. But if we're doing sine, we select the positive root, the second coordinate. This is a good spot to pause because once again, in my opinion, this is the nastiest part of the half-angle formulas. Any questions at all so far, folks, with what we got here, the positive sign? Okay, well, if we're happy with our sign, the good news is we're going to throw cosine theta right there, but we've already resolved what cosine theta is. We'll just put 3 root 11 over tenths right in that location. So this one's just about done. We're definitely going to need some space though, so let's throw that in. So on our very next step, we're going to say that this is equal to, I'll drop the sign. If we're using positive, we don't have to state a positive sign. And we'll go 1 minus, and usually you want to make that a little bit longer because we have to simplify on the inside. It's 3 root 11 tenths divided by 2. Sorry, say again? Oh, gotcha. What you'd want to do the next step, just to simplify it, is multiply by 10 over 10. That's going to clear this denominator, and it's going to turn into root 10 minus 3 root 11 divide by 20. At this stage, I'd say don't go too carried away with simplifying these things. There's no obvious simplification. Sure, you could break up the roots as root of 10 minus 3 root 11 divided by the root of 20, simplify that root 20, rationalize it further. But in these kinds of larger problems, I would say this is a very, very natural stopping point. It's pretty simplified already in that format. And trying to rationalize it further can sometimes make it look worse than that. But we did it, folks. That's sine of alpha over 2, provided that sine of, I keep saying alpha, let me try again. That's a theta. Sine of theta over 2 turns into that giant mess of a monstrosity, given that sine theta was just negative 1/10. If you do a half angle, weird things can happen with this stuff. But at least we have the exact value now. Any questions at all, folks, with that one there? Okay, well, that's 1 down. Next, we need to do cosine of theta divided by 2. The good news, though, is when you do this computation, you're pretty much doing the same exact thing. You do have to change the sign, so let's carefully write out cosine theta divided by 2, let's double check our sine chart above. At theta divided by 2, cosine takes this negative value right here. So I'll write out as plus or minus, but this is the actual sign we'll be selecting, the negative sign. And the rest of it goes like this.
Why is it negative?
Only because of theta over 2 terminating right here says that the cosine value should be the first coordinate, which takes on this negative value on the x-axis. Yep, you betcha. But it's definitely tricky because of that theta right there coming out as positive. Other questions so far? Okay, then from here on out, pretty much what you want to do is essentially, not completely, but essentially copy what you just did. Let's take a look at these identities again. Note, these are practically the same identity. The only difference is the sign right here. You use the positive sign if it's cosine alpha over 2, and you use the negative sign if it's sine alpha over 2. Because it only differs by a sign, well, this becomes a 1 plus cosine theta, but we know that that's a 3 root 11 tenths divide by 2. So only thing I've done here is I've taken the negative sign and converted it to a positive sign because we're using the cosine half angle formula. We reduce it the same way by multiplying 10 over 10. And then it comes out as pretty much the same answer, just 10 plus 3 root 11 20ths. That's kind of nice in a way. These identities are so very similar that if you've done the sine version, you've essentially done the cosine version. Just change the negative sign here to the positive sign there. And in fact, if you duplicate your answer like that, I'd say that'd be acceptable. Except I did make one mistake now that I'm looking at it. Anyone see the mistake that I did honestly make on that, right by the red dot? Yep, I said we should use the negative sign. I circled it, but then I didn't copy it. So don't do as I did. Make sure you copy in that negative sign. We could, and we used that strategy back up here when we were doing the double angle identities. We calculated sine at 2x, we calculated cosine 2x, so we just observed tangent at 2x, just throw them on top of each other and simplify. That's where it goes sideways really, really bad, because if you take those prior two answers and form a fraction like this, that's the, well, it might not be terrible, but it's a tough simplification. Thinking about it, you know, maybe not the worst thing in the world. So if you did go that route, you would get a pretty decent answer. The downside is it may not be the actual answer the back of the book gives. So that's the only reason I provided this identity right here. I've noticed in the back of the book, this is what they're really doing when they go to simplify. But I'll give you an offer though. It is correct to say tangent, this is step 3, of theta divided by 2 is simply going to be this version divided by this version. So if you go that route, I would accept it for full credit. But let's try out this identity, since that's usually what you're going to be looking at if you're checking your answers. So this turns into sine theta 1 plus cosine theta. And that means if we go this route, the work is actually quite a lot easier. Let's see what happens. We already knew the value of sine theta. At the top of the problem, it was negative 1/10. Then 1 plus, we found the value of cosine theta. Cosine theta was calculated to be 3 root 11 tenths. And the simplification here is just far, far easier to work through. What we want to do is reduce the fact that it's a complex fraction by multiplying 10 over 10. And you're probably expecting that. We did that in the prior answers as well. We just extend that radical sign. So when we go to simplify this one, in the numerator here to here, that's negative 10 over 10 for a negative 1. In the denominator, we'll get a 10 here, plus here, that's going to be 3 times 10 root 11. The 10 cancels, and you just get 3 root 11. So there it is, folks. That's our answer. Any questions at all getting to that stage? Okay, well, last one. 4 asks for cotangent theta over 2. And that seems a little bit nasty in a way because I never defined an identity for it. But it's actually not as bad as it seems. Any volunteers for what we should do to get cotangent? Exactly. We just take that last answer, good call, and flip it. The reciprocal would be 10 plus 3 root 11 over -1. Because -1 is dividing, it's going to flip both signs in the numerator. It'll be -10 minus 3 root 11. So the reason I put this fourth part with cotangent is just a reminder that the reason you don't see an identity for cotangent is because of what we just did. There really is an identity, just take the reciprocal. In fact, let's just write that in. Cotangent of alpha over 2 would be 1 plus cosine alpha divided by sine alpha. Well, any questions, folks, on running through these versions here? Sorry, say again. Oh, we get the actual theta from this stuff? That sounds about right. Yeah, this is a pretty small y coordinate, so really small rotation. And it was a rotation in the negative direction, right? Oh, gosh, gotcha. Yeah. Yeah, that's another pretty good way to solve that because if you could just get the angle, now you can input it into these values and just calculate them directly like that. If you needed exact values, that's when you'd be doing it this way so that you don't have approximations. Well, any other questions or comments so far, folks? Okay, well, let's try this all again. Let's carry this half angles formula down. And this time, we're going to do a function evaluation. I mean, we kind of already did, but what I mean by that is this time we know the angle, and we're just trying to get the value sine 9 pi over 8. Let me insert a little bit of space here. Here's where their standard reminder is that even though it's called a half angle formula, what you're really doing when you use the half angle formula is you take the angle and you double it. That's what we have to do exactly right here. But even before that, we have to resolve the pluses and minuses. So we need to get a good sign chart going to decide what is the value. Let's maybe start by just putting in sine 9 pi divided by 8. By formula, it's going to go plus or minus the square root 1. Oh, and that's a mistake. If it's sine, you have to go minus right there. Let me try again. 1 minus cosine of something divided by 2. But again, here's a reminder. When you actually go to use this formula, you do this. You take your 9 pi over 8. Doubling it just means times 2. So we would just get 9 pi over 4 on that thing right there. Sorry, say again? Gotcha. So let's put in, right in this location, a 9 pi divided by 4. I found that this is pretty confusing. How does folks feel about going from the 9 pi over 8 to the 9 pi over 4? Does that make sense on that stage? Awesome. So I guess to me, the reason why this is kind of confusing is when it says half angle formula, it just feels weird that you're doubling the angle. The fact that it's a half angle formula is just because there's alpha over 2 here is the only reason it's named as such. So now that we get here, next thing we need to do is come up with a sign, plus or minus, and find the right one. It's the same pretty much strategy. We do a really fast unit circle. That's probably going to be the best one I draw all semester. I'm kind of proud of that one. That actually looks circular. And we want to find somewhere here a close angle we know to work with. 9 pi over 8 is really close to just pi. That's a good place to start. Give it a denominator of 8. This is 8 pi over 8 now. And now 9 pi over 8 would mean you're rotating pi over 8 degrees further in a clockwise direction. So the terminal angle would be right out here. Now that we got that, we need to look at what are we calculating. We're calculating a sine function. So that means it's going to take a sine on the y-axis. The output is right there. And now all that work just to say we're using a negative sign on the very next step. So I'll go here and let's circle that negative sign. I'll try to remember to copy it next. So there's a lot of stuff that goes on with this. First thing we did is we wrote down the formula. We doubled the angle. Then we did an analysis over here to find the right sign. And now the problem is about ready to get going. This is all equal to negative square root 1 minus, and I was about to put in cosine 9 pi over 4, but really what we should do is just calculate that right now. Anyone happen to know where 9 pi over 4 would terminate on the unit circle? Which quadrant? Start drawing these just to make sure we can find it. If you're not sure, it would be quadrant 1. Good call, absolutely. So 9 pi over 4 would be right here. If you're not sure, you're pretty much just counting them. This would be 3 pi over 4, 5 pi over 4, 7 pi over 4, and then 9 pi over 4. We're doing a cosine now. There's always a cosine right in here, the doubling the formula. So that will output to root 2 over 2. Positive is the major thing we were looking for. This negative sign still survives, and we're just substituting in a root 2 over 2. And the whole thing is divide by 2. So it doesn't look like we wrote a lot, but we really did a lot. This is a pretty technical identity to get through. Any questions so far, folks, to that stage? Okay, next thing we'd want to do is just simplify this thing. So here's where you'd probably multiply by, say, let's make it 2 over 2. Only reason I'm multiplying by 2 over 2 is I'm trying to clear that 2 right there in the root 2 over 2. I usually put parentheses right here to distribute. And now we get to negative. This will be 2 minus root 2 in the numerator. When 2 distributes through, we get a 2 there, and it cancels that denominator. Down below, we get a root of 4. And so this is a rare problem where it would simplify a little bit more naturally. We could say that this is equal to negative root 2 minus root 2. I mean, that's kind of funky to look at. It's a nested square roots inside here. Then take the root at the bottom, root 4. And that's our simplification. The whole thing is negative root 2 minus root 2 halves. So now sine 9 pi over 8 outputs to that right there. Kind of wild in a way, but any questions, folks, to that stage? That's a good question. This is what I would do personally to check my work. I'd go to pretty much just any calculator. This will do the job for us. And first thing I would do is, let's put in sine 9 pi over 8 to just see what it evaluates to. I believe Desmos is in radian measure, so I would trust that answer right there. Let me double check. And we're expecting negative, so that looks about right. Then we'll compare that decimal expansion with what we put here. So go negative square root 2 minus square root 2, divide by 2, and check all the decimal expansion values. This is not a proof we did it right, but this is an extreme amount of good numerical evidence we are on the right track at least. So that's what I would do each and every time. And I would be wanting to buy a lottery ticket if I saw a match here and a match here, but I really did make a mistake on that. It can happen, but that would be fantastically rare. Well, any questions, folks, on the check or running through the problem? Okay, so with that problem done, that's our last set of identities that we're going to take a look at majorly. But for the next set, I won't be asking any direct exam questions for this. This one does have a homework question. And the major reason that this is here is this one's really a calculus kind of problem. This is something that you would have to deal with in calculus because a function sometimes written in this form is just really hard to work with, depending on what you're doing. So just in case you're curious, if you know you're taking a lot of math, we need to rewrite this in order to integrate. And this is a problem that you would do in calculus 2. So it's way out there, but it's also a good reminder that if you're taking a lot of math, you'd be taking things like calculus 1, 2, 3, differential equations, linear algebra. Every one of those courses I mentioned use trigonometry everywhere, even linear algebra, as strange as that sounds. So the more you can retain from a trigonometry class, the easier all that coursework is going to be. Because the last thing you want to get bogged down in Calc 2 is issues about trigonometry. So here's our chance to see what this process really would look like when you do it as a calculus 2 problem. It says rewrite the expression sine to the power 4 of 8x with an exponent no higher than 1. Before we launch into that one, let's practice with this. Let's suppose you had a problem that went cosine squared of 7x. So if we want to write cosine squared of 7x with an exponent no higher than 1, that means we're using a reduction formula. If you look closely at these reduction formulas, let's say we've got to use this one, you might wonder where did it come from? But if you take this right here and square root it, you would get cosine theta. You now have to square root the right-hand side. You get two potential answers, plus or minus root 1 plus cosine 2 theta over 2. And that's the formula that we were just using, the half angle formula, because you go from here to here by doubling it. So it's really the same formula, but we're taking the square root off. We're squaring both sides in a sense. But now back to this problem, what we would do is write this as 1 plus cosine of something over 2 using this identity right here. Any volunteers for what should go into that location? Sorry, say again. It's definitely tricky because, I mean, we're looking at different variables, different formats for the same identity. But one thing to always note is no matter how you state these identities, you're always doubling. Oh, let me spell doubling correctly first. Even over here, you double it. And so back onto this one, you'll take the 7x and drop in 14x. So when we go to use a reduction formula, what happens is the power goes down. That's the reduction part. But the input to the cosine starts to get larger. We're doubling that every single time you use the formula. So that's our warm-up of the formula. Now we're going to try with this right here, sine power 4 of 8x. Good call, absolutely. That's the strategy here because it doesn't even look like you could do it, right? It's sine to the power 4, but these are all power 2. But just like you said, the more you do weird tricks with algebra, the easier this all gets. Take the sine power 4 of 8x, and you can re-express this as, just like you said, sine squared of 8x times sine squared 8x. Now we're going to do what we did with the cosine identity for sine, but we're just going to do it twice now. Does that make sense to folks on the start for this one? Okay, so following the color coding, here's where I'm going to use the identity. Because these are multiplied, I'll put parentheses around them as well. And notice the only difference between the reduction formula for sine and the reduction formula for cosine is the sign changes in the middle. The rest is identical. That's inherited from these identities, where the only difference was the sign in the middle here and here. So back down to this one. will go 1 minus cosine. But what would you say should go right here? Any volunteers for that input? Exactly. You take the original 8x, double it for a 16x. Essentially, that's been our mantra ever since we moved past the double angle formulas. If you're doing half angle identities, reduction formulas, you're now doubling things. Then divide by 2, same exact thing over here. 1 minus cosine 16x. Divide by 2. Well, the next thing we have to do is start multiplying this through. If you look at the instructions to the letter, it seems like we've really done it, but there is an implied exponent. That's power 2 on cosine, which is implied. And in a calculus setting, this is no good to us. We still would have to expand all of this out and use a reduction formula again. So for the moment, all we're really doing is a lot of algebra. Let's multiply 2 by 2. That's going to be a 1/4. And now I'm going to FOIL across the numerator. So here to here is going to give us a 1. Here to here will be negative cosine 16x. Then do it again. Here to here is negative cosine 16x again. If you wrote down negative 2 cosine 16x from the start, then good on you. That's a really good shortcut to take. Then here to here, negative cosine times negative cosine will give us positive cosine squared of that same input, 16x. So that's the expansion. I put the 1/4 out in front, but you could have just left a big fraction bar and 4 down below if you like. In fact, probably the next step thing we'd want to do is just distribute 1/4 through all that. So let's go and write this as equals 1/4 minus 1/4 cosine 16x minus, oh, and I forgot to combine those. We'll do it on the next step. Minus 1/4 cosine 16x again, plus 1/4 cosine squared 16x. So I have a couple things I need to do. I definitely should have combined the like terms earlier. Usually you want to combine stuff first before you expand through. It simplifies your work. But also, that has an exponent higher than 1. So we'll use this identity once again to reduce it. So on the next step, first I'm going to take 1/4 as it is. Negative 1/4 minus 1/4 of that quantity is negative 2/4 of that quantity, which is cosine 16x. So because the power is the same on both of these, those are the like terms. We couldn't combine this one only because of the power 2 there. That makes it the non-like term of the bunch. So continuing on, let's go plus 1/4. And now finally we'll use the identity for cosine. Essentially the same for sine, you just put a plus right there. It'll go 1 plus cosine. We'll double the input of 16x to now get a 32x. And then divide the whole thing by 2. So we pretty much did the instructions to the letter. We have no exponent higher than 1. We have 32x as a trade-off, but this problem is more amenable to calculus methods, even though it's way expanded. That's one thing that's weird about simplifying. Simplifying always depends on the context that you're working in. But it's not fully simplified. Let's keep on working this through. You can divide both terms here by a half to get 1/4 minus, we can reduce this fraction here to 1/2 cosine 16x plus 1/4 multiplying. I'm going to take this 2 and divide into the numerator to make a half plus 1/2 cosine 32x. So everything we're doing here as from this stage on is just pure algebra. We're just trying to simplify what we have as much as possible. Next step, I'm going to copy up to where the red dot is. Then distribute 1/4 inside. Here to here would be plus an 8. And here to here would be plus 1/8 cosine 32x. Oh, I deleted too much there. Let me fix that. Any questions, folks, so far? Okay, well, we're nearly there, but there's still one last issue. This is kind of unfortunate. We still have a like term. The 1/4 and the 1/8 have to combine. Let's work that out in the margin. The 1/4 just multiplied by 2/2 for a 2/8. And we'll get a 3/8 out of that. So last step on this one, I promise, we get all together that sine to the power 4 of 8x is truly 3/8 minus 1/2 cosine 16x plus 1/8 cosine 32x. And we're finally there, folks. Somehow, some way, if you're taking lots of math, you'll discover why. In calculus 2, this is not good. That's hard to work with. And this thing is actually the simplified version, that big mess down there. That's why sometimes in math classes we do weird math. Usually there's a purpose, and I felt like it was good to mention on this one. I won't ask this as a real exam question. It'll just be for homework to help with calculus down the line. Well, we did it, folks. This is the end of the notes on all the identities so far. We're skipping section 7.4 that has more esoteric identities. They're not used very often in calculus settings. And so when you go to study for the upcoming exam, the trigonometric identities that we're working are pretty much everything except for these last two right here. I included them on the document, trigonometric identities on Moodle, just for the sake of completeness. If you're curious what those remaining identities are, here they are. Amazing. The way they proved all these is they really just grabbed your sum and difference formulas and did some really creative retuning of them to come up with more and more identities, the ones down below. But that's it for this section. Congratulations, folks. That's pretty much all of the trigonometric identities that we're going to be picking up in chapter 7. Next thing we're going to take a look at is equation solving. But I won't take up too much time in there since this next section is a really touchy one. Here's how it starts out. And I'm opening it up as a PDF because I definitely want to restart anything we do here. This is a really tricky section that deserves our full attention. I'd hate to do some work and then come back to it over a weekend. But the first issue that we're going to have to deal with is we're going to solve equations where we want to find all solutions. Oh, excluding the imaginary ones. Yeah, all real valued solutions is the ones we're going to find. But when it says find all solutions, we have to now use the fact that cosine is periodic with period 2 pi. So we're looking first for principal solutions between 0 and 2 pi. But then because of periodicity, we start multiplying by the right quantity to pick up all solutions. That's why there's some weird notations up above. I feel like this is very familiar to folks in this class. We've stated it a couple times. If you want to indicate the set of all real numbers, we use that fancy symbol right there, referred to as the chalkboard bold R, because it's hard to write bold on a chalkboard, I guess. If you're using complex numbers, you'd write the symbol in this format. And trigonometry does in fact intersect with complex numbers in chapter 8. But if you're trying to find all solutions, the set you really are going to be working with in this section is the set of integers z. Z comes from the German word of number. It starts with Z. I forget the actual word. Anyone speak German by chance? We can look that up later, but that's why it's Z for all integers. It's written as a doubly infinite set. So it starts at 0, go to the left forever, the counting integer is negative, to the right forever. We use this set to express all solutions. So we've got a couple minutes. Sorry, say again. These all for the German word? Gotcha, interesting. So from the German word, probably pronouncing it wrong, dissolve. Oh, gotcha. So that must be it. ZHAL for integer in German. That's kind of interesting, actually. Oh, switch those around, so ZAHL. So they take that and come up with a set of integers like that. The French and German have a lot of footprints on mathematics because of their early pioneer work hundreds of years ago. So now let me give you a preview to how this is going to work. A good section to review to help out with this is section 6.3 on inverse functions. Not because we're necessarily using the inverse functions, but it's more the process we're going to take. We draw a unit circle, then we take this number, negative root 2 over 2. Because it's a cosine, we want to place that on the x-axis. It would be about here, about negative 0.7. Now we need to reverse engineer what angles between 0 and 2 pi do we come up with negative root 2 over 2? Well, you couldn't just draw them. There's one up here. There's one down there. And this one is 3 pi over 4. This one is 5 pi over 4. These are referred to as the principal solutions to this function. It's definitely not all solutions, because recall, cosine's periodic with period 2 pi. This is very tricky, so we'll repeat this when we come back on our Tuesday's class. I mean, that's a long weekend as well. But we're about ready to state the solution. It will be x equals or x equals, because we found two principal solutions that correspond to negative root 2 over 2. We'll have two branches of infiniteless solutions here and here, separated by or. We write down what we found: 3 pi over 4, 5 pi over 4, and then we go plus, plus. Next, we are using periodicity. We know these things just repeat with period 2 pi. So we go 2 pi, 2 pi, and that still gives you another solution. But that's just one additional solution unless you do this. Exactly, we need an integer. We go 2 pi k, or any symbol you like, k, where k is in z. That means k could be 0. You get 5 pi over 4, 3 pi over 4. K could be 1, negative 3, 7, 29, anything like that. It just can't be a half. That's not an integer. The moment you put in this k value, you are now generating all solutions. So that's the process, and it is tricky. So we're going to spend extra time in section 7.5 just to see how all these ideas go together. So any questions at all, folks, with this first look at the process? There's definitely something exciting going on outside of the hall. Okay, well, I think this is a good stopping point for us. This might have been kind of fast, but we'll go over these ideas again. And with what's going on in the notes, first at example 1, we'll do several equations where we're finding all solutions. But then on example 2, we're going to find specifically the principal solutions between 0 and 2 pi. Well, I think this is a good stopping point for us, folks. If you have any other questions, I'll be happy to help out. Otherwise, have a great weekend. If you're working on the weekend, don't hesitate to write. I'll be happy to help out as well. Take care, folks, and I'll see you all next Tuesday. Thanks, folks.